Lesson, would you get out your trapezoid notes so we can continue on to those? Here we go. I think we left out here unequal subdivisions on your trapezoid notes, which are some color I don't remember. They're blue. Okay. Now, there are a lot of reasons. Oh. There are a lot of reasons you might use unequal subdivisions. You're welcome. One is they might give you a table with unequal subdivisions. Another is you might be finding the area under something where not all numbers are pretty. For example, if I said, hey, find the area under 25 with 5 trapezoids but no calculator. Well, if I had a calculator, I'd just divide 25 by 5 and I'd square root 5 and square root 10 and we're all good, yeah? But if I say no calculator, you don't know the square root of 5. You don't know the square root of 10. So you'd have to go more like 1 at 1, and then at 4, and then at 9, and 16, and they would all be different kind of trapezoids. You follow me?
Yes.
Okay, so the point is there are a lot of cases where you get unequal subdivisions, and you need to be able to deal with it both ways. So, the problem is that pattern of factoring out the h over 2 and getting the 1, 2, 2, 1 deal, that's out the window because there is no common h. I guess I could take out the half, and that's fine, but there's no common h to all the trapezoids to factor out if they're all unequal. So there's no GCF, and instead, you really just have to do each trapezoid separately. So, with that in mind, would you answer that multiple choice question? I'll answer this multiple choice question, and we'll see if we agree. How are we doing? Should be just about downers. How are your arithmetic skills? Are they solid or are they rusty?
Rusty.
Shame. Your elementary school teachers did all that work so you could blow it away. Okay, what'd you get? A, B, C, D, or E? It is B. Hey, how'd that go? Are we good?
Yeah.
Okay, that is.
I'm not there yet.
Oh, that is not super conceptual. If you can find the area of the trapezoid and you're decent with functions, you should be fine there. It's not hard. All right. Now let's go on to would you, by way of practice, would you go to extra practice tonight's homework number 4 and try extra practice for tonight's homework number 4? Did you get 79 and a half? No? 159 over 2? Okay. 150. Oh, no, 79 and a half, my voice. Puberty, you know. All right, are we good? Moving on. Okay. So, next concept, we kind of touched on this in the problem in the warm-up. It'll be good. Recall when using a Riemann sum, which means rectangles, yeah. You can tell if the estimate is over or under the true value based on the combination of
second derivative and first derivative.
Okay, not concavity. Okay, so here, would you draw me a increasing concave up and an increasing concave down? Yeah? Okay, if you used right rectangles in this first subinterval, which is going to be greater, the right side or the left side? Why? Is it because it's concave up or because it's increasing? It's because it's increasing, the right side is bigger. Okay, how about here? When you go from here to here and draw right side, which one's bigger, the right side or the left side? The right side, because it's increasing. In other words, for rectangles, concavity means
Nothing.
nothing. It is zero to do with it. I don't care if it's concave up or concave down. What it has to do with is, are you using right hand or left hand, and is the function increasing or decreasing? That's all that matters. Concavity does not matter for rectangles. So it's a combination of left, right, and increasing, decreasing. For example, it's an overestimate because I used right rectangles on a, what kind of function would right overestimate? Increasing. What else would cause an or an overestimate? You used left on a decreasing, because then the left side would be function, okay? Okay, cool. Now, would you sketch a curve and let's go concave, increasing concave up and then increasing concave down. And if you were to do a trapezoid here on the increasing concave up, trapezoids would overestimate. But here, trapezoids would underestimate. So what attribute of a function affects the trapezoids over or underestimating? Concavity. For trapezoids, it's all about concavity. Okay, so would you, actually, let's save our time here. Is this important? Yeah, do it, please. Do this problem. It's just good practice. Let's assume equal subdivisions here. Right? Did you get 22 as I did for the estimate? Okay, is this an over or underestimate? Overestimate, because the curve is concave up. Okay, so 22 is an overestimate because the curve is concave up. You follow? Okay, cool. Now, let's talk about how much of an overestimate. Now, this is actually the gold standard for estimation. Estimation is a huge part of higher math. It's not always the case that you can find the exact answer, and so you have, by the end of Calc 2, you have literally dozens of estimation methods that you could use. And besides having good estimation method is to have a companion to that to know how good your estimate is. That's the idea of error bound. Now this is a big part of Calc 2, so I'm going to really hit this hard, but it goes like this. Building off this idea, when estimating area using trapezoids, there are actually 3 factors that contribute to how much error your estimate has. So remember the big idea. You're trying to estimate the area under a curve using some trapezoids. And so, give me one thing that'll contribute to error. How much? Okay, yeah, the number of subdivisions. We'll call that n. All right, what else? how, you almost said it, how concave, yeah? There's different degrees of concavity. There's, yes, it's concave up or down, but there's a big difference between that concavity and that concavity. This would have not much error. This would have a ton of error. So the degree of concavity, how concave, how much are the slopes changing? How concave up or down? What else? This one's the hardest to come up with because it's so subtle in that. Yes and no. Okay, you're on the right track. So imagine if I were doing the area under this curve and I told you this was from point 0.01 to 0.04. Would this area, would the number attached to this error be a lot or a little? Okay, what if I change this to 1 million? And to 4 million. Now does that number represent a really big area or small? Okay, so the magnitude of the numbers of the region also matters how big the region is. Let's talk in each of those cases, direct or indirect. The number of subdivisions, is it directly related to the error or inversely related to the error? The more subdivisions, the more error, or the more subdivisions, the less error?
Inversely.
That's inverse relationship or negative relationship. How concave? The more concave it is, the more error?
Yes.
So that's direct relationship, yeah? And how big the region is. The bigger the region, the more error, or the bigger the region, the less error? That's direct. All right, so now we're not going to develop this formula because it's actually really, mean value theorem is used all the time in proof in calc. So after you take your first 2 years of calc in college, then you take the same classes all over again, but in theory, and you prove all this stuff. It's really pretty crazy. But when you go to prove this idea, you can show, really by use of the mean value theorem, that the error in the estimate, which when I say the error, I'm talking about how much off we are because we're using trapezoids instead of the true area, is less than or equal to, now this is called the error bound. It is not the error, because obviously if I knew the error, then I would go back and figure out the true answer, and I wouldn't have error at all. It's a bound for the error. I know my error is not more than this, and it comes down to really 3 components and then some extraneous stuff that comes from the proof that we're not going to get into. But B minus A, that's the region width. How big the interval is, it directly relates to how much error. In a direct way, the bigger the region, the more possible error. The number of subdivisions, that's n, that's an inverse relationship. The greater number of subdivisions, the less error. It's in the denominator. And the concavity, it's really a measure of just, we take, now the concavity actually is usually changing all over the place. So we use what's called M, which is the greatest possible concavity measure in the interval, or some cases a logical upper bound. M represents a maximum. M is a max for the second derivative on the interval. And would you parenthetically write that after that, or an upper bound? I'll explain more on that when we get into it, but let's take a look at this curve problem. If we use 3 trapezoids to estimate this area under the curve, now certainly I understand it's integrable, and you're probably thinking, why estimate this at all? Why don't we just integrate and find the exact, right? We can't throw you under the bus right away. We can't do one that's hard right away. We practice on an easy one so that the idea is there, and we'll gradually build up to the kind that you would have to use trapezoids for. The reason you use trapezoids at all, remember, is not everything can be integrated. Sometimes you get a function that's so crazy or funky or the exponents don't work, you just can't integrate it. So stick with me. I know that integrates. Believe me, I know. We're just going to practice this on an easy one. You with me? All right. Would you first give a 3 trapezoid estimate to that using equal subdivisions? bound, did you get 45 over 2 for an estimate? Okay, cool. All right, let's talk about the error bound part now. The error without respect to sign, you know, obviously we are going to know if it's an overestimate or an underestimate if I look at the second derivative, but we typically just say the error without respect to over or under is less than or equal to b minus a cubed over 12n squared times m. Let's do this in pieces. Let's put in the b, the a, and the n first, and then we'll talk about the m in a second. Okay, so let's break it into chunks. B minus a, what is it for this? 3 minus 0. Okay, that's the region width. N, what does N stand for? 3 stands for number of trapezoids, which in this case is 3. All right. The 12 is always there as part of the formula. The cube and the square, they're also pretty cool to see when you get into why they're there, but that's for maybe another day. But doesn't this boil down to 1 over 4 m, if I clean that up, yeah? All right. So m is meant to represent what's the greatest possible concavity that could be going on in this interval to get me some gap between the curve and the trapezoid. So if the function is x cubed, then the first derivative is 3x squared, and the second derivative is 6x, yeah? The max of f double on the interval, the greatest rate at which the slopes change is it going to be at 0, at 3, or at an interior point? 3. And so we would say that m is 18. We could say that's the greatest rate at which the slopes are changing, and therefore causing the curve in the curve. So if I throw that in there, then my error is not more than 18/4 or 9/2 on either direction. Now that would tell me that the value of this integral would definitely have to be less than 45 halves plus 9 halves. It's got to be less than 54 halves, and got to be more than 36 halves. It's got to be in that window if I use the error. What is the true error here? Something like 81/4. Do you agree? So what is the error here? Our estimate is 45 halves or 90/4. The true error or true area is 81/4. So the true error is really 9/4. Yeah. Is our error then less? Is 9/4 less than 9/2? It is. Okay. So remember, that's not the error we found. It's a bound for the error. I know my error is not more than 9/2. You follow? Okay. Let's try this from a different angle. Sometimes you are required to find a degree of precision. If you were to try and estimate this integral and you know you have to get it less than 1,000th off, well, the first thing you have to say is, all right, to get that close, how many trapezoids would I need? This is a different type of question, same idea. If we had to get error under 10 to the negative third, then how many trapezoids are required? All right. So we need, what are we looking for then? If I want to figure out how many trapezoids, I need to find n. I need to find n so that my error is less than 10 to the negative third, or 1,000, yeah? How many trapezoids do I need to get that precise? You down? All right, so where's the error bound go? This is a common source of error here, or people put things in the wrong place, and it's because they don't really understand what they're doing. They're just trying to go by memory, all right? Wouldn't you agree that we know the error is less than this, b minus a cubed over 12n squared times m, yeah? Now, if my error bound is less than 1,000, then won't the error also have to be less than 1,000? So if I could just get my error bound below 1,000, then I'm good to go, because the error is less than the error. You follow? All right. Now then, I focus on this. B minus A is still 3 cubed. And N, now you don't know. And M, well, it's still the same interval, the same derivative, the same second derivative, so M is still 18. All right? You down? Okay, so if I do a little solve for this, N squared is, I'd have 3 cubed and 18 and 1,000 in the numerator and 12 in the denominator. If I move stuff around, I move the n squared over, multiplying both sides by n squared, and the 1,000 over. And you should always be worried when you have an inequality, should I switch the sign, should I not switch the sign? Tell me why I don't have to switch in the sign. There's no chance of negative. N squared is definitely positive, 1,000 is definitely positive, we're all good. Cool? All right then. If you slap that in your calculator or clean this up and then slap it in your calculator, whatever you prefer, what do we got there? Something like 81,000 over 2 or 40,500 square rooted. So, what is that? 20 times 10, 200-ish. It's probably 200-ish. Somebody? Yep. Really what I was looking for. Yep. I was looking for a little help, but I think, yep, it's more than 200. 200. Yep.
You sure do know that.
201.246. Now, obviously, then that's stupid to say. I need 201.246 trapezoids. So, do I just round to the nearest and say 201 trapezoids, or do I need to go all the way up to 202? Yeah, you need 202 or more, obviously, trapezoids to get error less than 1,000. Excuse me. Done? Okay. Now, thankfully, they don't ask us to actually do that estimate, because that would really stink. And that would be worth actually writing a program for and calculating. That's for another day. Now on set 95, we should be able to do all parts of 6. You might have done some of set 95, number 6, but got stuck on the last question or two because it was error bound. If that's the case, then you can just pick up where you left off. If you didn't get started on number 6, the idea was the area under x squared from 1 to 4 using 4 trapezoids for A. Find the exact area using fundamental theorem for B. And then error bound for part C and D. All right, so now that we have that error bound idea, we should be good on part C and D. I'll let you work on that a while. Talk it over with your math amigos. Oh man, n equal 4? No, n equal 4. Life is ugly, get over it. Delta x is, I didn't want to say that. Oh,
Also, one criticized Mr. Cable's
so we're starting at 1 and going up 3/4.
I have a plan for a future.
confident with that one.
Two. Because it's two running it's two.
Why didn't I just choose?
Use logic. I know.
$381. Oh man, I hope that's right. I got 381 over 32.
I got 681.
681?
Yeah.
Dang it. What did I do wrong? That seems
Did
really
you-
small.
Is X squared?
Oh, you
Did you square them?
I definitely squared them. Alright, so what'd you say it was 6 what?
81.
No, because of
Dang
fours.
it, over what?
So you didn't do fours. Technically, you can do that after this, but you do fours.
You said multiply it by 3/8.
So to make it smaller.
Yeah. Huh. Alright, anyway, 681 over 32 seems pretty common.
Answers by democracy.
You guys had a calculator, so I trust you.
I reject your reality and substitute it with my own.
We got the
Inside the walls of this padded cell, anything is possible. My mental world yes. This also means
Okay, our estimate is a little more than the true, yeah?
Yes.
Does that make sense?
Sure.
Why?
Concave up.
Curve is concave up, so, yes, okay. Answer is greater, so that's good. I just added that in, I don't think it's part of it. Did they say it's part of it? Yeah, they did, that was just something I added, I just wanted you to see, it makes sense that we're getting an overestimate. All right, now C then, try C on your own, let's see if the error idea is sticking.
Like this cafeteria, mashed potatoes on the ceiling.
Oh, shoot. Would you go back to your notes, sorry? And in this box, it should be M is the logically chosen upper bound on the absolute value of F double. I don't care if it's concave up or concave down. I just want to know what's the maximum concavity measure.
Okay.
That should be on the second derivative's absolute value.
Oh, that is an error. Don't worry.
into the weekend, it's like time for a break. And then it's one right before school. Homework. When it was like.
So what is your error bound? This 3 equal to 9/32. Okay? The error is no more than 9/32. Now try D.
It's like, when you push something this where it's
Oh, it's not really good. That's really hard.
no. I just thought I don't remember now. It must not
It still sounds like really big.
feel like anything for kids.
Oh, it's the number of stars. It's like, that's a really big
It
error.
goes fast. Keep speeding up.
Wow, you actually did that. That was a lot of fun. So I just
No, it's
seriously, I led on to this problem. I did sticky math. I have to do that a lot where it's like, hey, I needed extra room because one thing about our math program is
no, we'll do lowercase
it's like in college and I'm like, it's lowercase a. I can't hear. It was
no, but lowercase a is an one yeah, that's just an upside down view. Just like all the time.
So what did you say? You need at least? What did you say, people?
67.
That's 68. You would need at least 68 traps, always round up. Okay? Even if you have the smallest decimal. Alright? Okay. Number 12. Go to number 12 on the homework.
I definitely remember looking at this and going,
I'm sorry,
Well, I think I changed it to
wait, what does it want the balance
Okay, yeah, it's for you to figure out if you're not going to use a calculator, where are you going to subdivide?
I did pi over 6, pi over 4, pi over 3.
Okay,
And then there's two equal subdivisions.
might help you to think of these as 2 pi over 12s, 3 pi over 12s, 4 pi over 12s.
So glad we could figure this out. Thanks, dude.
Alright, make sure I get 6. This, whatever it is, 95 at the end of the day, please.
Okay, it says today.
Yes.
What
Should
about
have done
the
it.
4 thing? 94 this thing. What?
What?
Did we turn this in?
Sure did, yes.
A long time ago. Extra time. This was a long time ago. I was told to come on.
If you didn't turn in 90, oh, you were taking the test. If you didn't turn in 94 extra practice, turn that in today, please.
Yeah, because I did.
Yeah, I just remember looking at a lot of those problems and going, Not especially